closed. But before that, as the part of reading course, I have already mentioned that few of the students who are very good teachers, I'm sure, that going to show how good are they in teaching. They are no doubt very good students, and they are going to teach us now the different. Today we have Mobius functions and Mobius inversion formula and all. So may I now request the speaker or the teacher will be the next teacher, will be the next speaker maybe.
Sir, I might start
Okay,
first.
okay. So it's now your turn. So I'm sharing the screen. So please share. I am stopping my screen sharing. So it's now your turn to
Okay.
start the presentation. Yes.
So is my screen visible now?
Yeah. So can you just a bit introduce yourself, who are you, and you
Yes,
are
yes. First
studying
of all,
here.
thank you so much, sir, for such a lovely talk. And throughout this whole course, you have been such a great teacher for us in this semester. And I am Subhradip Palchaudhuri from Presidency University in third year of BSc Mathematics. And I'm going to talk about Mobius function. And my fellow classmate Pratik Roy and me, we will try to uh, take everyone who are listening as much close to Mobius function as we can. And I will start, then he will continue from where I will leave. So should I start, sir?
Yes, please, please. Now it's all yours.
Oh,
Two
thank you.
classes.
So first of all, Mobius function. It's named as after August Ferdinand Mobius, this function was first published in one of his papers in the year 1832. And 30 years before him, Gauss also wrote about this, not naming this function, but wrote something that is pretty related to it, and but didn't carry it on. So we will talk about Mobius's work first. What he actually did in 1831 was he created three different bins to and he planned to put the natural numbers in those bins, following the characters of the numbers. He made three bins, which are the zero bin, the positive one bin, and the negative one bin. And he put the numbers which are multiples of square numbers in the zero bins, such as 4, 8, 9, other than 1. Definitely 1 is also a square number, it's square of 1. But he didn't put 1, except 1 he put all the multiples of square numbers in that zero bin, such as 4, 8, 9, 12. 12 is divisible by
Sorry,
4.
sorry to interrupt, but his skin is, I think, is not visible. You presented.
Yeah, I probably presented it. Is it
No,
not?
it's not visible. Yeah.
Oh, okay. Sorry. So let me share the screen first. Oh, sorry, I forgot to share the screen. Is it now visible?
Yes.
So now the article is visible, right?
Yes. Now
Yes.
it's visible.
Okay. So what I was talking about, he created three bins, and in the zero bin he put all the numbers which are square of which are multiple of square numbers, such as 4, 8, 9, 12, 16, and so on. And in the positive one bin, in the negative one bin, he put all the numbers which are if we prime factorize the numbers, we get odd number of prime numbers as the factorization of the number. That is, if we know that for any natural number n, we can prime factorize it. That is, we can write n as product of pi power alpha I, where pi's are distinct primes and alpha i's at the power of pi's in n. But we have already considered a bin, that is zero bin, where we put all the numbers which are multiple of square numbers. So if any pi has power 2 or more, then we put that in the 0 bin because it's a multiple of square numbers. So we are only left with the numbers which are of the form product of pi, where pi's are distinct primes. So in this case, if I runs from let's say I runs from 1 to k, and if k is an odd number, odd positive integer, then we put that number in negative 1 bin. And similarly, if k is an even number, then we put that in the positive 1 bin. And that is how we will define the function, the Mobius function, as mu. We write the Mobius function as mu, such as mu runs from mu is from natural numbers to complex number, as mu of n is 1. If n equal to 1, we define it differently for 1, and is 0 if p square divides n, that is if n is a multiple of a square number, and minus 1 power r if n equal to p1 p2 dot dot pr, where pi's are distinct primes. So there we can see there are r distinct primes product up to n. So minus 1 power r is nothing but minus 1 if r is negative, r is odd number, and is plus 1 is if r is an even number. And that is how the Mobius function is defined. And the bin concept that I talked about is the beginning of defining the Mobius function. What apparently Mobius did actually in the year 1831. Now we know that an arithmetic function is a function from the set of natural numbers to the complex numbers, and a multiplicative function is a function such that it follows the property f of mn equal to f of m and f of n, where GCD of mn equal to 1, or mn are co-prime numbers. So now as we have defined the Mobius function, we can easily prove that Mobius function is multiplicative. And the proof is pretty obvious. We define m and n such that they are co-prime, and we consider one of m and n without loss of generality. If one of them is a multiple of a square number, then mn is also multiple of that square number. Then it is mu of mn becomes 0, and if let m was divisible by a square number, then mu of m was also 0. So mu of mn is equal to mu of m into mu of n. So this is obvious. And if not, if none of them are divisible by any square number, then we can prime factorize m and n in this way. Product of pi's, where I runs from R1 to R, and qy's, n as qy's, where I runs from 1 to s. And if both r and s are odd integers, then they sum up to an even integer. So that means individually the mu value of m and n are minus 1, but when we take mu of mn, it becomes minus 1 square, which is plus 1. And we can consider 4 different cases, and in all the cases we can easily see that the statement follows. So mu is not only an arithmetic function, but also multiplicative function as well. Now we are going to define a very interesting what we say binary operation as the Dirichlet product, which states that for given two arithmetic functions f and g, the Dirichlet product of fg is the summation of d divides n f d g n by d. Now we are going to try and prove that this Dirichlet function, this Dirichlet product operation forms a ring with respect to the set of all arithmetic functions. So for that, first we need to let's not see the first part. Let's move on a little bit downwards, and let's see if the operation is commutative or not. We can prove that this operation is commutative, and we know that if d divides n, then we can write n as d dash, where d dash is also an integer. So we know that d divides n, so d dash is n by d. So if d divides n, then it is easy to see that d dash also divides n, because d dash equal to n, so both of d and d dash divides n. So in that way, if we can understand that, then it is pretty obvious that f of g of n, we can replace d with d dash, and it becomes fd becomes m f n by d dash, and g n by d becomes g d dash. And we can see that f of g n, f product of g n is nothing but g product of f n. So it is a commutative binary operation. Now, is this associative? So for that, we consider a couple of uh, variables, such as if let us say that d dash is a number which divides d and d divides n. So from that, what can we say? D dash divides d. From that, we can write d as d dash k, where k belongs to a natural number. K is a natural number, and as d divides n, we can write d dash k divides n. That implies that k is divides n by d dash. So this replacement is very important when we are going to prove the associative property of the Dirichlet product. Here we can see that summation over d dash divides d divides n is nothing but summation over d dash divides n, k divides n by d dash, which we just proved in the previous slide. Now we, as we do, consider three arithmetic functions f, g, h, and we first we check f product of g, product of h. We break that into d divides n and f product of g d, h n by d, and then in the f product g part, we again break it, and we consider d dash divides d as it is f compose g d, not n. And here we find a summation d dash divides d divides n. We can certainly from there write d dash divides n, k divides n by d dash using this replacement, and from there we replace d by d dash, and finally we come to a stage where it is pretty obvious that it is an associative function, associative binary operation, and we find f compose g compose h n is nothing but f compose g compose h. So we proved both the commutativity property and associativity property. Now we are going to find some arithmetic function which plays as the multiplicative identity for all the arithmetic functions with respect to the Dirichlet product. Let us consider the function delta n, as the delta n value is 1 if n equal to 1 and 0 for n greater than 1. So for every natural number except 1, it is 0. Now check that f of delta n is nothing but delta of fn, as we have shown that this is a commutative binary operation, and then the d divides n, fd delta n by d is nothing but d divides n. We break the summation as we consider the divisors of n which are less than n, and at last we consider when d is equal to n. So f1 delta 1, fn delta 1 is nothing but fn, because delta 1 is 1, and for every value which is not 1 delta n, which is not 1, delta n is equal to 0. So the left part, the summation part, will give us nothing but 0. So f Dirichlet product of delta n is fn. So this gives us this proves that delta n plays as an multiplicative inverse for all the arithmetic functions with respect to the binary operation Dirichlet product. So now we can see that the set of arithmetic functions forms a commutative ring with identity with respect to pointwise at with identity, and which is that identity? That is the delta in function with pointwise addition and Dirichlet product or Dirichlet convolution. Now let us talk about the um, okay, now we will prove that the Dirichlet convolution of two multiplicative functions are multiplicative. For that, we need to, as we did in the Mobius function part, we will do the same thing. We consider two numbers m and n which are coprime, and two arithmetic functions, arithmetic multiplicative functions fg, and we Dirichlet product them, and from there, as m and n are coprime, so any divisor of mn, which is d, we can write it as d1 d2, where d1 divides m and d2 divides n. As m and n are coprime, they don't have any common divisor except 1. So d1 and d2's gcd will also must be 1. And then we just break the fd1 d2 part as fd1 into fd2, as f is multiplicative. We do the same for g, and then we break the summation and find that the Dirichlet convolution of two multiplicative functions is multiplicative. Now we will prove a nice little property that mu of 1 of n. So what is 1 of n? One function is nothing but the function which gives us one value for every natural number n. So 1 of n is 1 for all n belonging to capital N. So mu of 1 of n, which is nothing but d divides n mu d into 1 of n by d, which is 1. So summation d divides n mu d equal to delta n, that delta function we previously defined. So for this, we first start with considering a prime number p, and let us consider for n, where n is p power k, where k is greater than 1. So we first consider we first going to try to prove the proof for a natural number which is a power of only one prime, p power k. So for this, the proof is pretty obvious, because the summation d divides p power k mu d can be written as mu1 plus mu p plus summation I equal to 2 to k mu p power I. And we know that for p square onwards, p square, p cube, p power 4, mu of these values are 0, because p square divides all of them. So that summation part will give us 0. And mu1 is 1, as we know right from the definition, and mu p is minus 1. So this gives us 0. Now, as the function mu Dirichlet product of 1 is multiplicative, and why is that multiplicative? Because we know that mu is multiplicative, the Mobius function, and we also know that one function is also multiplicative, because 1 of mn will give us 1 equal to 1 of m into 1 of n, which are also 1. So 1 of every number is 1. So this function is clearly multiplicative. So that implies that the Dirichlet convolution of these two functions will also be multiplicative. So for any natural number n, where n can be written as the product of pi power ki, we can break the if we consider fn as the function to summation of d divides n mu d, then we can break fn as f pi power ki, product of f pi power ki, because it's multiplicative and all the prime numbers are co-primes. So we can break them, and which will give us 0, as for each prime f of pi power ki is 0, we just showed previously. So whenever a prime number divides n, we find that fn gives us 0. So what if n is equal to 1? Then this will not be 0, because then the functional value of f will be mu1, which is 1. So only for 1, this is this gives us 1, and for every value which is greater than 1, this gives us 0. and that is the definition of the function delta. Delta also gave 1 for n equal to 1 and 0 for n greater than 1. So this function is nothing but the delta function. Now we have shown quite a few properties, and we will move on to the Mobius inversion formula. But before that, let us see the Mobius function with quite a few examples. So mu of 1, as we see, it is 1. Mu of 2 is what? Mu of 2 is nothing but the prime. If we prime factorize 2, it will give us 2. So this is a product of one distinct prime number with power 1. So this is nothing but minus 1 power 1, which is minus 1. Similarly, for mu of 3, it will be minus 1, because 3 is also a product of one distinct prime number. But what about mu of 4? Mu of 4 is 2 square. So this will give us 0. And now if I ask you what is the value of mu of 0, then what will it be? Anybody from this class, if you want to answer this? Mu of 0 is what? Okay, so mu of
Mu is not defined for 0.
hmm?
Mu
What?
is not defined for 0.
Exactly,
Mu
mu
is
is not defined for 0. As we first defined mu, it was an arithmetic function, and an arithmetic function is defined from the set of natural numbers to the set of complex numbers. Here we can see, so 0 doesn't belong to the set of natural numbers, so mu is not defined for 0. So mu of 0, we can't answer anything, we can't say anything about mu of 0, because it is not defined. So yeah, that's absolutely right. I think it was Rajibul. Thank you, Rajibul. Okay, so now we will move on to the Mobius inversion formula. Now this is one of the most important parts of the of our article, the Mobius inversion formula, which states that if capital F and small f are two number theoretic functions, number theoretic functions are the same as arithmetic function, is just another name. If the capital F and small f follow the relation as capital F n equal to small f Dirichlet product of 1 n, that is capital Fn is the summation of d divides n small f d, then using the Mobius inversion formula, we can say that small f n is nothing but the Dirichlet product of mu and capital F of n, which is the sum over d divides n capital F d mu n by d. Now this is a very useful theorem or formula, which we will use in solving some problems also later part of this article. And in this is the application of this formula is pretty high in the field of studying Mobius functions. And so before going to the problems, we will try to prove the formula, and it is not at all tough. We as we have done the harder parts, we have proved many things before in this article, so it won't be that tough. Had we had not proved those things before, then we might have some difficulties in proving this formula, but now it will be pretty easy. Let us see. We know previously that mu of 1 of n is nothing but the delta n function, we just proved. So we can write mu Dirichlet product capital Fn, and as mu of Dirichlet product small f product 1 small f product 1 n, because it is given in the problem. Then we use the associativity property of Dirichlet convolution, and we take mu and small f together, and then we use the commutative property on them, and we replace it, and then we again use the associativity property to take mu product of 1 together, which will give us delta, and delta plays as an identity to all the arithmetic functions with respect to the Dirichlet convolution, and this will give us small fn. So the left hand side is equal to the right hand side. So the proof seems pretty obvious and clear, I think. Any questions regarding this proof, or whatever I have said so far in this talk? Anybody? Any questions? Okay. So now we will just like the sum parts, we can prove the same result for the for products too. How? We just let capital Fn as the product of d divides n small fd, and similarly we can from the Mobius inversion formula say that small fn is nothing but product of d divides n capital F n by d power of mu d. This time the as it is a product not sum, the mu part goes into the power of d. And this proof is also pretty obvious. If we see that we from the left hand side we break the capital F part, which give us d dash divides n by d small f d dash, and then we take those products together, d divides n, d dash divides n by d, and then we just replace that product as we know that if d divides n, if d dash divides n by d, then we can say that d dash divides n. So both d and d dash divides n. So we just replace d by d dash there, and we can do that because if d dash divides n, then both d and d dash divides n, as well as d divides n by d dashed, and d dashed also divides n by d. See, if we write that, it might sound a bit confusing, but if we write that, we can easily see that d dash this divides n, right? Now from here we can say that d divides n and d dash divides n. Can't we say that? We can, surely. And now as d dash divides n, we can also say that d divides n by d dash and d dash divides n by d. So that's what we used. It's not replacing them. It's the same thing. Writing d dash divides n will imply all of these things. That is what we have used there. And we have a nice little chart to show for an example too. So we will look at that later. No, we will look at that right now. That will be more helpful. For let us see for the example n equal to 6. So what are the divisors of 6? The divisors of 6 are 1, 2, 3, and 6 itself. Now, if we here we have written C and D. So consider C as D dash and D as D. So look at that if D divides D dash divides N, so we pair them as D dash. So look, 1 6 is a pair, and if we multiply them, which gives us 6, divides 6, right? Again we look at another pair 2 3. If we multiply them, 6, which divides 6. If we consider 2 1 pair, multiply them, which gives us 2, divides 6. So for all d dash divides n, that is for all the pairs which the multiple of those pairs divides 6, we can consider the vice versa parts. So for the pair, consider 3 1. 3 1 multiplies to 3, which divides 6. So we can say that 3 divides 6 by 1, as well as 1 divides 6 by 3. So all these relations are true whenever we find two divisors of a number which is product is also a divisor of that number. These all relations are valid then. So we use that relation, and we take the d divides n by d dash part inside, and here inside means the power. the product of this will give us the sum in the power, and sum of d divides n by d dash mu d will give us nothing but delta n by d dash. Now if d dash is anything less than n, any proper divisor of n, so this will give delta of n by d dash as 0, because n by d dash is greater 1. That will imply that if d dash power 0 gives us 1. So the only case which will not give us 1 is when d dash is equal to n. Then this will become fn power mu of n. Fn power delta of 1, which is 1. So the product finally gives us fn, and that is what we had to prove. We needed to prove in the first place. So the Mobius inversion formula is also applicable for the for products of for two arithmetic functions, capital F and small f. Now I am almost nearing my end of my parts of the talk, and Pratik will carry on from now. The last thing I need to show you, this is also a very important property which we will use in solving problems. That is, whenever we find a function that satisfies the relation if Dirichlet product of 1 is the function delta, then this f must be equal to the mu function, the Mobius function. There is no other function except the Mobius function that satisfies this criteria. So this is a very important result. To prove that, we first let us assume that except the Mobius function, there exists another function, as we usually do in solving this kind of problems, another function f which satisfies this relation. Now we can write the Mobius function mu n as mu Dirichlet product of delta, as delta is the identity, and then we can replace delta by f of 1, as we have considered there exists a function f which is not the Mobius function which satisfies that criteria. Now we apply the associative property on them, and then the commutative property, and then again the associative property to find that gives us nothing but f product of delta, which is f. So we find that the mu function is nothing but the f function, or vice versa. The function we let is giving us the function mu. So this is a contradiction, as we primarily let that f is not equal to mu. So this proves that there doesn't exist any other function except the Mobius function which satisfies this criteria. Now we will talk about some interesting applications or some interesting problems where we will need the Mobius functions and the Mobius inversion formula. But from here on, I will ask my fellow classmate Pratik Roy to carry forward. This is his part now. So any questions regarding my talk, whatever I have said so far? Any questions about them? Is there any confusion in the definitions or the examples or any proof that I have shown so far? Please feel free to ask me. Okay, so thank you. I think everyone has understood whatever I said so far. I hope so, and I will ask Pratik to continue with sir's permission. Sir, that this is the end of my talk.
Okay, thank you, Subhradip, for a nice and illuminative talk. You are a very good teacher, no doubt about that, and I hope that all the students of the remaining class also enjoyed your class. So now it's time for Pratik to please start your presentation or the class teaching, not exactly the presentation, but class teaching. So in this course, we try to rotate this thing so that many of you will have some experience of how to teach and all. So that's quite important to be a teacher in future, or even to work at any place, because talking habit we should have some kind of habit that we can talk fluently or we can make others understand quite easily. So that's it's a kind of practice. You may be a good student, but not always that. In my experience says that it's not always that a good student can also teach in a nice way. But it requires some practice and thinking also. So I'm sure that Pratik, in the next presentation or class, he is going to give a excellent talk like Subhradip has already given. So it's up to you. So Pratik, it's yours now. Pratik, can you hear me? Pratik,
Yes,
are you
sir.
here?
Network
Yeah.
problems.
Okay. Okay. No problem. So please start.
So is the screen visible?
Yes, visible now. Yeah.
Okay, sir. So first of all, I would like to thank on behalf of the members of our group, Kolpo, Rajibul, and Subhuti, whom we all heard, who familiarized us with the Mobius function. To sir, to like to thank sir to give us the opportunity to present our article. So now, as Subhudeep has familiarized us with the function, so it's my turn now to give some applications or some uh, areas where it comes up. So application would be a bit overrated because it is not a logic or a particular idea that we use. It is just a function which is used to clean things up or to make the messy things a bit prettier. So, so the first problem I would like to start with is the necklace problem. The problem demands that we have k different colors of beads in an unlimited supply, and we want to know how many necklaces of length n can be formed. So, first of all, I must define what do we mean by distinct necklaces, because we want to count the number of different necklaces. So, what is the meaning of the different necklaces? What is the basic characteristic of distinguishing them? So, first of all, the one criteria that we must follow is that we are assuming that we are arranging the beads of a necklace on a tabletop. So, we are concerned with one face. Otherwise, there will be ambiguity on from which side we are seeing, and that would result in the same necklace having two mirror images when written on a paper. So having that said, let's start with the problem. Okay, so now I have some pictures here to elaborate. Okay, so these type of problems are these are combinatory problems, and they are very easy to deal with. Some examples first for giving us some motivation about how we must proceed or in which direction we must go to get the answer. So at first I have dealt with the two extreme cases. Okay, so what are the extreme cases will be? The first case will be the monochromatic beats. Monochromatic beats means all the beats are of same color, and the other extreme case would be all the beats are of different colors. So if all the bits are same color, that the problem is very easy, because there will be, if there will be k colors, then there will be k different necklaces, each with beads of a particular color. So I have said here, I have shown an example for n is equal to 4, where there are 4 beads and there are 2 colors. So we can see that there will be only 2 necklaces, one with blue color and another red color necklace. So in general, we see that for case 1 or the monochromatic one, we have as many necklaces as the colors, and hence the answer will be K. So it will be simple. And for the other extreme, we see that if in this example or for the drawing, I have taken n equal to k equal to 4, or there are 4 colors and there are 4 bits, and all of them are of different colors. So I see that there are 6 distinct necklaces. And then the next question that one might ask is, what gives us the confidence of saying these are the only necklaces possible? So I have written there corresponding string arrangements. String arrangements mean I have cut the necklace between cut the necklace just before the red one. So to understand the problem, I have fixed the red bead at the particular position, that is the top position, and I have just cut before the red one. So, and I have cut it and I have written it in a linear arrangement. So I see that, as we can also predict from or count directly, there will be 24 arrangements, because there are 4 different things and there are 4 different places where we can put them. So it will be 4 factorial arrangements, which is nothing but 24 arrangements. But there is one catch here. These 24 arrangements are not all representations of distinct necklaces. We see that if we place each, or if we denote each of these distinct necklaces as the linear arrangements, we see that a circular permutation or just a shifting permutation by I mean that one right shift and then bringing the last one to the front. If we perform that operation, that would yield 4 different strings. But all these strings in the for example, in the first row, or in each of these rows, these are 4 distinct strings, but all of them give only one necklace. So as we have this problem just turns out to be a problem of circular permutation, and we have already dealt with circular permutation. That is, there are 24 string arrangements, and each of these, if we take one representative of this string arrangement, that it will represent one necklace, and all 4 of these represents one necklace. So every 4 represents one necklace. So how many necklaces will there be? It turns out to be simply 24 by 4. That is 6, or it is 3 factorial. That is n factorial by n, or n minus 1 factorial. So this also turns out to be pretty simple. And for general case, if we have suppose k colors, which is for different beads having different colors, k must always be greater than or equal to n. Here, for example, I have taken k equal to n, but in general k can be greater than or equal to n, and all the beads have different colors. So at first, what we must do is that which n colors I want to use, that I must choose first. So that can be chosen in k choose n ways. And once I have chosen the n colors that I want to give the beads, or color the beads, I can then arrange those beads or colored beads in n minus 1 factorial ways. So the number will be k choose n into n minus 1 factorial ways. We can check it if we put n and k to be 4, that turns out to be 4, choose 4, that is 1, and 4 minus 1, 3 factorial, that is 6. So we have dealt with the 2 extreme cases. So now what happens if we are dealing with something in between? So in this example, I have taken n to be 4 and k equals 2. I have taken 2 colors, 2 possible colors, and I have 4 beads for the necklace model. Okay, so we are dealing with polychromatic necklaces, to be precise, and not only any polychromatic, but I don't only restrict to all the necklaces to be different of different color. They can be different, they can be same, and there is no restriction. Okay, so a naive calculation, or in general I can say that as there are 4 beads and each bead has 2 choices, so it will be 16 to the power 4 by multiplication principle, and from the observation that each bead has two choices, or in other words, the number of binary sequences of length 4. So that is true. That is true if we are talking about linear arrangements. But if we get the corresponding necklace arrangements, I have grouped them. We see that this the groups I have named as O1, O2, O3, O4, O5, and O6. The reason for behind naming them O is a bit involved, because not involved because it is intentional, because these things will turn out to be orbits of some things. As I will go on later, I will explain how can these be orbits of something, or why they are. But for now, they are just some sets. I have grouped those necklaces into some particular sets. Okay, so the first set has all colors same, and second set also has all colors same, and the third set has 3 colors blue, which are consecutive, and 1 red. I see that all these 4 necklaces in the O3 group or the orbit 3 group, they are the same necklace, but only a circular permutation of one another. So all those they have different string arrangements that I have written at the below their respective necklaces. They have different string arrangements, as we can see from here, but all of them represent the same necklace. And the same is the case for O4. They have different string arrangements, but they represent the same necklace. And same is for O5 and O6. So there is something going on here, apart from the number of bits and number of colors. There is a particular role played by the arrangement that we are implementing on the necklace. By that I mean that how we are placing the beads and which bead is placed after which. And another observation I must make here is that we see that in the orbit 6 group and orbit 4 group, both of these have 2 blue and 2 red colors, but they have different number of they have different members here. They have, for example, O6 has 4 different string arrangements, all representing the same necklace, but O4 has only 2 different string arrangements representing the same necklace. So this prompts us to think that not only the colors, not only the number of colors that is important, but how the colors are placed after each other is also very important, and we must look deep into it to understand the problem, or to understand why the overcount is happening. And this understanding this, I will go back to the write-up once more. Okay. So this prompts us, as we have seen, that there is something going on with the linear arrangements that doesn't only involve the number of colors we have taken, but also the way the colors are placed after one another, or the particular arrangement. This prompts us to define one thing, that is a period of a string. So what is the period of this? So what is the period of the string, the first string in the group O4? We see that the string in arrangement of period O4 has only 2 periods. Period as period 2, because after implementing the right shift twice, it will come back again to the first arrangement that we started with. And for example, in the group or in the subset O3, we see that there are 4 distinct string arrangements, and if we take the first string arrangement, and if we apply the right shift operation on the first string arrangements 4 times, we will return to the original one that we started with. So it has a different period. So there is something that is very much linked with the arrangement, that is the period of a string, that is the smallest number of times after which smallest number of times I have to apply the right shift operation to get back the original one that we started with. So that prompts our definition that we define here. The period of a string, the smallest number of right shifts required to get back to the original string, also counting the identity shift, is called the period of the string. Hence, any string of period D would give D distinct strings under the action of the shifting function. And that is very much clear from the drawing here. The period is D, period is 4 here, and they give 4 distinct string arrangements. And here in case of O4, the period is 2, and they give 2 distinct string arrangements. So that is pretty much clear here. Okay, now another claim, or that is an intuitive idea that we might have from these examples that we manipulate for some small numbers, and we might observe that at each time we see that the period divides the length of the string. So we might investigate, is it true for general case, and pretty much it is true. That can be proved easily if we take n is equal to dq plus r and assume that r is a remainder. Nothing to assume, I mean r is a remainder which is from 0 to d, and we must prove that, or at least we want to prove that the r is 0. Okay, so let's start with it, and I have denoted the function f as the right shift function for notational purposes. And we know that the right shift function has period n, because if we apply the right shift operation on n times on any arrangement, as the length of the arrangement is n, after n times it has to come to the original arrangement that we started with. So it has order n. and we know that Fn is Fdq plus R. And what is Fdq plus R? But it is a, and this operation that we are doing is composition. So Fdq plus R can be written as Fr of Fdq. Now we have demanded that D is the period of this arrangement. So obviously, applying the right shift operation of multiple times of the period, we'll get the original arrangement. So we get that Fr of Fdqa is Fr. Now, what we have now is that Fra is equal to A. We started with A and we are getting it equals Fra. But here is the problem. If R is a positive number which is less than D, and we have Fra equal to A, that means applying the right shift R times, we are getting the original one. But that contradicts our definition of the period of the arrangement that we started with. So R must be 0 if this has to hold. So hence we have proved that the period D, which was a mere hunch of ours, that it must divide the length of n. It is true, in fact. Okay, so now there is a main thing that we want to, we have just taken a reroute from what we are trying to prove at first to define some stuff which will help us, or at least help us to understand or makes the notations clear for the proof that we proceed afterwards. Okay, so for the time being, let's just ignore the red one as the color mentions. Okay, so now so we want to find that what is the number of necklaces. We know that we have already observed that each necklace has a distinct string arrangement. Now each string arrangement has certain periods. So my aim is to count the number of necklaces by counting the number of strings and accounting for the fact that how many different strings give the same necklace. Okay, so my job turns out to be counting this number of strings, but in a certain order. I want to count the strings grouped in a particular way. I want to count them by their periods. Each string must have a period, that is obvious, and that period must divide n, that we have already proved. So every string has certain periods, say D. Now if I take a string of period D, I have seen that this string and its other D minus 1 distinct arrangements of this string would yield one unique necklace. So the contribution of these D many strings is 1 to the number of necklace. So and this is not true for any particular string of period D. This is true for any string of period D. So the number of necklaces which is contributed by all these strings of period D is the total number of strings of period D by D. So we have taken into account all the necklaces that is formed by strings of period D, and that turns out to be strings of period D by D. And we just sum up these contributions over all such Ds, and we know that every such string would fall into some D which divides n, and so we have accounted for all the contributions of the different strings having different periods. Now we have found this. We still don't have one thing or one information at our hand, that is what is the number of strings of period D. So our next aim is counting the number of strings of a given period. So if we see that we perform the same counting for the finding these strings of period n, but in a different way, or here the overcount is different. You see that if we take a string of length n, we want to find the number of strings of length n. Each of the string of length n would be have some period D, and any string has some period, and so I want to count the number of strings by their periods. So summation D divides n, number of strings of period D gives us the total number of strings of length n. This is pretty much obvious because this scheme, that is if we take the set of all such strings of length n and we are counting it, I am imposing a partition on it. What is the partition? Two strings belong to the same partition if they have the same period. Okay, so I have partitioned the entire set of strings of length n, and each partition has a particular period to it. All the strings of partition period d belongs to one partition, and I'm just counting the cardinality of each of the partitions. So that must always give the entire cardinality of the entire set. So that is pretty much what this line says. Okay, so now we have an expression for strings of length n, but we still don't have an expression for strings of period d. So here here is the place where the Mobius function comes up, and it is a perfect model for applying Mobius inversion formula. So to clarify the calculations, because there is a step jumps here, so let's see the calculations a bit. Okay, so if we define Fn to be to start with, we must define some number theoretic functions, because we know that Mobius inversion works only for number theoretic functions, but so far what we have said, these are only some non-mathematical terms we have used. So let's use some mathematical terms for those non-mathematical things that we have said earlier. Okay, so we have defined Fn for strings of length n. We know what is Fn, because any string of length n means it has n bits, and each bit has only k choices of colors that we have established when you started the problem, that there are k choices of colors available, and each of these bits have k choices. So what will be the number of strings, total number of strings? That will be k to the power n by multiplication principle or of counting. Okay, so we know what is Fn, that is k to the power n, and we define Gn to be strings of period n. We see that both f and g are arithmetic functions, and what we had previously for the expressions of strings of length n and necklaces of length n is written in terms of mathematical notations, and it turns out to be that necklaces of length n, which is Fn, is equal to necklaces of length n equals to summation d divides n gd by d. One thing must be kept in mind: Fn is not the length number of strings of length n. It is the number of strings of length n, not necklaces of length n. So this thing and Fn are two different things. Necklaces of length n and strings of length n are different things. Okay, so we had that number of necklaces of length n equal to summation d divides n strings of period d, that is gd, number of strings of period d, that is gd by d. And we also had that number 2 equation, Fn equals to summation d divides n gd, that is number of strings of length n equals to summation d divides n strings of period d, that is written in mathematical terms Fn equal to summation d divides n gd. Okay, now we can apply Mobius inversion to get that Gn equals summation d prime divides n for some d prime mu n by d prime f d prime. So at last we have some expression for the function Gn, that is strings of period n, and that is what we wanted. And we can just place this the expression for Gn in Gd of equation 1. So what will be Gd? Just we can replace n by d, and we get the formula for number of necklaces of length n as follows. That is summation d divides n 1 by d gd. What is gd? Gd is summation d prime divides d mu d by d prime f d prime, and that turns out to be this expression: summation d divides n 1 by d summation c divides d mu d by c k to the power c. Okay, so as of now I have an expression for the number of necklaces of length n with respect to mu. So what is the helpfulness of this expression? So one helpfulness of this expression is that if we observe carefully, this is some analog of the principle of inclusion exclusion, because in the principle of inclusion exclusion, what it tells us how much we have to add and how much we have to subtract, because the accounting of the overcount involved in a counting problem is one of the most difficult parts that confuse us. And for that, the principle of inclusion exclusion doesn't simplify our calculation, but tells us a systematic way of how we can proceed counting it. It doesn't simplify the calculation remains the same, but it just tells us how much exactly what we must subtract and what we must add. And this mu function here, as we know, the mu function can give +1 and -1 as answers. It's in some way just tells us when we have how much we have to subtract and how much we have to add. But this is not the famous expression that we have for necklaces of length n. We can go a bit steps further to get a feel of this problem, because this problem seems, the necklaces problem as we have presented here, seems a much complicated problem with some messy notations, and this expression mu is not very pretty, because as I have stated that these are we have written this as the applications of the Mobius function, but the word application would be a bit overrated, because Mobius function is not any particular idea. It's just a function, and it just makes things prettier. Look as it makes things compact to write. So we look a bit deeper into this expression. Okay, so returning. Okay, so we again define certain number theoretic functions. What we are doing here is just simplifying our expression. So we define f1n as the function k to the power n. Now this k to the power n is a arithmetic function surely, because this is a function from the set of natural numbers to the set of natural numbers. So it is obviously a number theoretic function. The same is the case for in. In is basically the identity function, not the identity operation or identity function of this Dirichlet operation, but the identity function as such, it gives the input as the output. Okay, so now observe that we had an expression like this: summation c divides d mu t by c k to the power c. My claim is that I can write it like mu star f1d, and it is pretty much obvious from the definition. Nothing to claim about. Okay, it is pretty much obvious from the definition that you have presented, right, of the Dirichlet convolution, and it turns out simply to be mu star f1d. Okay, from Gauss we know that we know the famous identity that summation d divides n phi d is equal to n, or in other words, in the form of Dirichlet convolution, that turns out to be I equals to phi star 1. Phi is this Euler-Toscan function, and it just tells us phi n is the number of positive integers less than n which have GCD 1 with n. Okay, so this is I equals to phi star 1. Okay, now we had the expression for the number of necklaces a bit similar to this one, only this n was not here. The summation we had summation d divides n 1 by d, and then summation c divides d mu d by c k to the power c. I have just multiplied an n here. This n doesn't influence the sum because it is a constant term. It doesn't influence any of the indexes that are running here and there. Okay, so I am trying to simplify this expression. Okay, so I can write n by d as summation d divides n I n by d, because I n is n and I n by d will be n by d. And this expression here, as I have written it before, is mu star f1d. So what this complicated sum turns out to be is I star mu star f1n. Okay, and this expression is a bit helpful because it is compact, nothing else. Okay, now we already know that the inverse of mu is 1, or one function by mean I mean that 1n equal to 1 for all n. It is also an arithmetic function, and mu star 1 is equal to delta that we have seen earlier, or in that talk that Subhradip presented, the part where Subhradip presented, we have seen that mu star 1 equal to delta. Okay, so what this expression is, I'm just trying to simplify this expression. That expression is I star mu star f1. Okay, I star mu star f1 can be written as the expression. I am just substituting the value of I that we have proved earlier, that I from Gauss we know that I equals to phi star 1, and phi star 1 star mu star f1, and I have just used associative property here, and it turns out to be phi star 1 star mu star f1, and 1 star mu is delta, and then we have finally phi star delta star f1, and you know that this delta is the identity function, element of the ring of arithmetic function under pointwise addition and Dirichlet convolution. And so delta star f1 is f1 for any f. Delta star f is f, so delta star f1 is f1. So phi star f1 is equal to this I star mu star f1. So what this complicated sum turns out to be is if phi star f1n or summation d divides n phi n by d k to the power d. So if we divide n from both sides, we get that the expression for the number of necklaces that we had before with respect to mu and all other stuffs, it turns out to be a simpler. Oh, okay, there is a mistake here. I have written here mu here, it's really phi. Okay. I have by mistake I have written mu here. So it will be 1 by n summation d divides n phi n by d k to the power d. Oh, I have written mu here by mistake. Okay, so we know if we ignore the last line, we see from the second last line the summation d divides n by d is equal to summation d divides n phi n by d k to the power d, and we can just divide n, so we get that number of necklaces is 1 by n summation d divides n phi n by d k to the power d, and this is much prettier and is also much more famous expression. And it is much more famous in another aspect, because it tells us it has something to do with some group theory. It is the first time we have a hint of something group theoretic happening here, because phi is a very group theoretic term, because it is a cardinality of some sets and certain orders. Phi pops up again and again, so it gives us at least a certain hint that there must be some bigger scheme of things happening or going on in this counting problem. So this or gives us an inspiration to dig a deep deeper. Okay. So we inspect it further, and we see that if we name the shifting function operation f, we observe that a cyclic group generated by this f under the composition operation of composition, or the notation is the circle, small circle, and if we take this group, we see that this group acts on the set of all arrangements. And what it does to the arrangements, I have shown it below. F acts on a1 to an, and it makes it an a1 to an minus 1. That is, it just performs the right shift operation. And f cube means I am performing the right shift operation 3 times. Okay. So here is a lemma that I am not proving it here, but it is not much difficult to prove. It's just counting in counting the same thing in 2 different ways, and I'm just using the lemma to give a group theoretic proof to this counting, and which can be generalized to other symmetric counting problems. Okay, so what the lemma says is that we have a finite group acting on a set, and if x, let the set be x, and let xg be the set of all such elements of the set which are fixed by this particular element of the group G, that is, elements fixed by the action of G. Then the lemma says the number of orbits is 1 by cardinality of G summation over all such elements of G of the cardinality of these sets, that is, the elements fixed by the action of G. And I see that if we have defined this action, and I have taken the set X as the set of all arrangements of the string arrangements of our necklace, we see that in this picture what we had written as O1, O2, O3, O4, O5 and O6, these are nothing but the orbits of the arrangements under the action of right shift operation or the function f. We see that all these strings that are in a particular subset or O3, O4, they can be obtained from one another, of a members of a particular set can be obtained from one another by performing a right shift operation, or performing some composition of right shift or certain number of times. So these things which we had as certain sets, these are nothing but the orbits, and so the name was given as O1, O2, O3, O4, O5 and O6. Okay. Okay, so I want to count the number of orbits basically, because I want to count the distinct necklaces belong to the distinct orbits that we can see from the picture, because we have said that each of these orbits have one representation for a valid necklace, and all the others are the same copy of the same necklaces, just a circular permutation of the necklace. And thus we want to count the number of necklaces. That was the problem, and that is equivalent to counting the number of orbits under this specific action on the set. Okay. Okay, I will be just quickly saying this because there is not enough time. Yes, so only thing I want to know is xg, or xg means that number of elements fixed by the action of G. Okay. If I know that, I know the cardinality of G, that is n. So the formula will be 1 by n summation G belongs to G, cardinality of xg. So only thing I must know is the cardinality of the set of, or the number of set of elements that are fixed by a specific element of the group. Okay. So for example, I have chosen a particular, I have denoted the right shift operation, and that I have taken n equals to 6. So f is 1, 2, 3, 4, 5, 6. I have taken the permutation representation of the functions to understand it better. Okay. So what is f square and x cube? I have denoted it here. So what happens if we say that we want to find x f4? I want to find, sorry, I have written f square here, that will be f4. Okay, so I want to find the elements which are fixed by the application of the f4 operation on the element. So if I have taken the element as this particular 1, 2, 3, 4, 5, 6, or this string, I have by 1, 2, 3, 4, 5, 6, I mean that the colors I have taken as C1, C2, C3, C4, C5, and C6. Okay, so my claim is that after applying the operation 4 times, I'll get the same thing, or the thing I have started with. So after applying the operation 4 times, I get 3, 4, 5, 6, 1, 2. And then just comparing, we see that the color of 1 must be equal to the color of 3, the color of 2 must be equal to the color of 4, the color of 3 must be equal to the color of 5, color of 4 must be equal to 6, and 5 to equal to 1, and the color of the 6th bit should be equal to the color of the 2nd bit. So summing up all the facts we have just derived from our claim is that C1, C3, and C5 must be same. That is, the color of the 1st, 3rd, and 5th bit must be same, and the color of the 2nd, 4th, and 6th bit must be same. This observation is much more clear if we see the picture at the right. We see that what happens is that if we apply this, and we must also observe what is the cyclic representation of this permutations. We see that if we take a particular representation or the particular bit and apply these permutations or the right shift operation, and we see that they have a particular cycle structure or a cycle decomposition. And we see that if we want a particular arrangement to remain same after we have applied the cyclic, after we have applied the right shift operation or this particular cyclic decomposition or particular permutation, is that the elements which remain in a which rotate or revolve in a particular cycle, they must be of the same color, because they are the ones which change positions among each other. So if we want them to remain same, they must always have the same color. So that is what the picture at the right says. It says that here the permutation is 1 is sent to 5, 5 is sent to 3, and 3 is sent to 1. That is F4 permutation cycle decomposition. Okay, so it must happen that the 1st bit and the 5th bit and the 3rd bit must have the same color, and the 2nd bit, 4th bit, and 6th bit must have another different color. Because if the 1st, 3rd, and 5th bit do not share the same color, when you apply this permutation, one of them will change color, and we will be able to distinguish them. So that our claim that after applying F4 on this arrangement, I must get the same arrangement that I started with is violated. So the element or the bits which remain in a particular cycle must always have the same color. So we see that the elements or the arrangements that remains fixed by this permutation is chosen by what type of cyclic decomposition this particular permutation has, or this particular right shift operation has. So we see that it doesn't only matter depend on the power of f, or the number of times I have applied f, because here that I have applied f 4 times, but yet I need only 2 colors. And I see that for f2, which has a cyclic structure, cyclic composition 1, 3, 5, 2, 4, 6, this also requires the same number of colors, distinct colors, 2, because we see that 1 is sent to 3, and 3 is sent to 5, and 2 is sent to 4, and 4 is sent to 6, and 6 is again sent to 2. So if I have to have that after applying f square, I must get the same thing back. I must have that 1, 3, 5 have the same color, because they are the ones changing position under this permutation. And 2, 4, 6 must have the same color, because they are changing positions among the other members. By that I mean that 2, 4, 6 will change positions with 2, 4, 6 only, and 1, 3, 5 will change places among themselves. So they must have the same color if we want to get the same arrangement that we started with after applying this operation. Okay, so this prompts us that the cyclic decomposition is the main important thing, and here are the calculations which I must I will just quickly say. Okay, so if we know that any permutation any of these operations or cyclic group has a cyclic decomposition like this, some has fixed length d, and there are n by d of them, and this d must divide n. Okay, so if our fi has a certain type of decomposition like this, as I have mentioned here, so I must have fi to the power d, that is fid is identity, because each of these cycles have period or order d. So I must have n divides di, which means that n by d divides I. So I is a multiple of n by d. Now what type of multiple n by d I must be? Can it be any multiple of n by d? So there is a restriction there. So if suppose f n by dt has same decomposition as I have stated here, that is cycles of length d each, and there are n by d cycles. So then I must have, if it has period s, then it must have n divides n t by d into s, that is d divides ts, which prompts us to say that if the GCD of d and t is not 1, then s, which is the smallest such number satisfying this condition, can be given can have the value d by d prime, which is strictly less than d. That is a contradiction, because we have assumed that this f to the power n by dt had a cyclic decomposition as follows. So I must have the GCD of d and t is 1. So how many those I are how many of those I are valid? Exactly those I are valid for which this t and t has GCD 1, and how many of them are there? That there are 5d of them. And from that I can just take the sum and then again group them according to their cyclic decomposition, and I can get the formula summation 1 by n summation d divides n phi n by d k to the power d. So my point in saying this is that this phi thing appearing here gives us a hint that there must be something group theoretic appearing here, or there is a application of group action that might occur here. Okay, so and why this k to the power n by d occurs here? We see that each of these d blocks or d cycles must be assigned one particular color. Okay, and how many of these cycles are there? N by d disjoint cycles, and each of these disjoint cycles can be given any color, but every member of a particular cycle must have the same color. So each of these n by d disjoint cycles have k possible choices, so they have in total k to the power n by d distinct necklaces. Okay, so it is just another way of proving the same thing, but in a much more meaningful way, rather than just hunting for the opportunity to get mu out of somewhere. Okay, so that was this problem. Okay, now another problem that just tells us another place where just mu comes up. Okay, and this problem tells us that mu n can be written as the sum of the real parts of the primitive roots of unity, that is summation k divides summation GCD k greater than or equal to 1, such as k and n have GCD 1. Okay, so if we define fn as this identity, the right hand side, so it is obviously an arithmetic function, because it gives the domain is natural numbers and the output is in a subset of complex numbers, so it is obviously a number theoretic function. And my first claim is that this identity or this identity, that is summation sum of all the roots of unity, that is summation k equals 1 to n I e to the power I 2k pi by n summation d divides n ft can be written as summation d divides n ft. Okay, and what is fn? And fn is just the identity that I have written before. Okay. So what I do here is that I sum over all the roots of unity by just grouping them according to their GCD, according to the I can denote e to the power I2 pi by n as some suppose I denote it by x naught. Okay, I say I denote it by x naught, and then all the roots can be denoted as x naught square, x naught cube, x naught 4, and so on. So all the roots are of the form x naught to the power I, and I am just summing these over all these roots based on the grouping them with according to the GCD with n. If GCD of I and n is D, I'm putting x naught I in that group. Okay, so just grouping and then summing up, I get that the summation d divides n GCD k comma n equals D e to the power I 2k pi by n. Now, if k and n have GCD D, obviously k is greater than or equal to D because D divides k, so it must be greater than or equal to D. So I can say that this summation can be also written as GCD k by D comma n by D equals to 1, and there is a certain substitution or just making it just adjust our some formula by introducing some substitution k prime equals to k by D, or you can do it just straight away from here, and we get that summation D divides n 1 to n GCD k prime n by D equals 1 e to the power I 2k prime pi n by D. So we see that this is just the same thing, but just n is replaced by n by D. The same thing we started with, for the expression of fn, and here we have just placed n by D. So this is nothing but summation D divides fn by D, and that is equal to summation D divides fd, which is because these two sums are equal because these are just summing up the same thing in two opposite ways. If we say that summation D divides n f n by D goes from left to right, summation D divides n fd goes from right to left over all the devices of n. Okay, so basically these are same, and we have
Yeah, Pratik, can you hear me? I think we lost the connection with Pratik maybe. Anybody else can hear Pratik?
No, sir.
Okay, I think connection is lost maybe. So I think he is going to join. So yeah, it was nice teaching. I think some connection problem might happen. Can somebody call him so that what happened exactly might be some power off or something. So Rudip, can you just have a look at what happened?
Sir, I called Pratik. He didn't follow that he was disconnected. He is coming soon. He is joining.
Okay, okay, fine. That's the problem with digital course. It's very difficult to understand whether you are connected or not, and
Yes,
it
yes.
may happen, and it happened with me as well. So sometimes I think that I am connected because you are basically telling in front of kind of mirror. Yes, he has joined. So just can you please tell him till how much he told so that he can continue and we can cut this. It won't be a problem. So while posting it in the YouTube, I just delete that part. So he should continue from where he left. That would be fine.
Okay. So, the was the part of the necklace problem complete? No, I didn't realize it when I was out.
Yeah.
Okay.
So Subhradip, can you tell him till how long he told?
Yeah, he was presenting that written part that he wrote in his copy.
Yes. So can you
He was
just
explaining that
show
part.
him?
The last part of the necklace problem.
The
Yes.
next, yeah, the last part. Right.
Okay. So,
So
what I was saying here is that we only needed to.
first, Pratik, present that screen first.
Oh. See, is the screen visible?
Not yet.
No, yeah, it is now.
So did I tell this part, this page?
No, it wasn't open while you were disconnected.
Yeah, this was the page, I think.
Yeah, this was the page. Yeah.
Okay, so here I was up to this point. I have already said that the main thing that was governing or our choice of which what type of how many colors are possible, or what are the total number of arrangements that are possible is that we have already seen one example here. Yes, so we wanted to find how many elements or how many arrangements are there which are fixed by the element F4 of the group, and you see that this F4 has a decomposition 153 and 264. So I have just applied this F4 on the particular arrangement 1 2 3 4 5 6. By 1 2 3 4 5 6 I mean these are the colors of the bits, that is C1 C2 C3 C4 C5 C6 respectively. So now if we apply F4 on this arrangement, that is F applied 4 times, we see that the first and the last arrangement must be same. So that demands C1 equals to C3, C2 equals to C4, C3 C5, and C4 C6, and so on. And finally, we have that C1 and C1 equals to C3 equals to C5, and C2 equals to C4 equals to C6. So that means that these 3 bits C1, C3, C5 must have 135 must have the same color, and 246 must have the same color. These two groups of 3 each must have the same color. They can share the color, but the members of each group must have the same. Okay, so this is also quite clear from the drawing that I have presented on the right side. That is, I have just presented the cyclic thing going on here in this arrangement, and as we see that one can only go to under this particular foundation, one can only go to 5 or 3, and the same is the case for the bit of number 3 and 5 also. They can only rotate or revolve around 1 3 5 only. And for 2 4 6 they can also rotate on 2 4 6 only. The 2 can go to 6, 6 can go to 4, and 4 can go to 2. That is, we see that the bits with having the numbers of this, or the bits having that these particular numbers 153 and 264, they will rotate according to their in their own respective cycles only. So if I want, or if my claim has to follow, that is after applying this permutation to this arrangement, the I must get the first arrangement that I started with, this the bits in the same cycle must have same color, because these bits are going to only 153. For example, you can take one can only go to 5 or 3. So 5, if it falls on 5 and 3 and it has a different color, then my claim is violated. So 153 must have same color. Similarly, 264 must also have same color. So it tells us there is something about the cyclic decomposition that works here, and not only the power of f that I am taking, or number of times I am applying this shift operation. Now, for example, if we take f2, or that is I apply the shift operation twice, that is which has a cyclic decomposition 135 and 246, I get that this also requires that 1, 3 and 5 and 2, 4, 6 must have the same color. So I see that the cyclic decomposition of the permutation representation of this shift operation function is what governs the main fact that governs the type of arrangements that are fixed by this particular shift operation. So I claim that if a particular shift fi, that is the member of the shift operation which is applied I times, has a particular cyclic decomposition as each of length d, and then there will be n by d disjoint cycles. I assume that it has certain this type of cyclic decomposition, where d is a divisor of n. Then I must have fid equals to identity, because I can apply this d times to get the identity, because each of these distinct disjoint cycles have order d. So n must divide di, and so n by d divides I. So I is a multiple of n by d. Now I want to see that does all multiple of n by d has this property, that is has this type of cyclic decomposition. So for that I assume that I take a multiple of n by d, that is f to the power n by dt, and I assume that it has period s. So if my claim is to be true, this s has to be d, or the smallest such s has that n by if n by dt s equal to identity must be d. So from that I see that if n by dt s equals to identity, n divides n t s by d, and from that I can say that d must divide ts, because otherwise I am dividing something from n and so I cannot divide it. So from that I claim that d divides, or I can get that, not claim, d divides ts. Now if t and d has some GCD d prime, then from d divides ts I can claim that d by d prime divides s. Then the smallest such value of s which satisfies all these conditions can be taken as d by d prime, but d by d prime is strictly less than d if d prime is greater than 1. So we must have d prime equal to 1. That is, all such t which has GCD with d equals to 1. So only those i's which have this criteria are capable of having this type of cyclic decomposition. And how many of them are there? So that will be just all those t which has GCD d with which has GCD 1 with d, that is phi d many. And I'm just taking the summation of these sets, just grouping them according to their cyclic decompositions. So, and we know that from the pictorial representation here, that each of these disjoint cycles must have the same color. Now each of these disjoint cycle has k choices, so, and there are n by d many disjoint cycles, so total number of possible arrangements will be k to the power n by d, because each of them has k many choices. So finally I get that for each of these or shift operations which has decomposed a permutation representation like this, that is has a cyclic decomposition of disjoint cycle of length d each, have total number of string arrangements that are fixed by those type of operations are k to the power n by d, and then k to the power n by d is a constant, so it can be taken out of this sum, and so it is basically summing up of 1 over all those such permutations. And how many of them are there? That is phi d. So that turns out to be summation d divides n phi d k to the power n by d. And we can just go back to the formula for Barnside lemma, it tells us it is the number of orbit is summation 1 by g. Here the g is the cyclic group of the generated by that shift operation that has order n. So 1 by g, 1 by order of g would be 1 by n, and this sum we have just found out to be summation d divides n phi d k to the power n by d, and that is what the number of orbits is, and that we have already seen before. As just it is just another approach or another or the main reason for coming this way while doing this problem is that it's more the expression that we had earlier with respect to mu is not a very famous expression. The famous expression, the famous part here is the phi. The phi expression is more famous. So I have just shown that that the same expressions are same by using some mathematical the identities of arithmetic functions. But I have just derived directly. I can just derive directly that the number of orbits is this 1 by n summation d divides n phi n by d k to the power d. The main purpose of giving this side of the proof is that this side is much more logical, or this side can be easily generalized to higher symmetric problems where the overcounting is very much messy and the symmetry is much more involved. So just to mention that, I have presented this side. Okay, going back to the writer. So I was saying about this problem. I have just start from the beginning. So the identity that now I want to prove is that mu can also occur in some pretty much applications of some complex numbers. Okay, so it is not very much involved operation. It is just a simple identity. What it says is that the mu n can also be interpreted as the sum of the real parts of the primitive roots of unity. What are the primitive roots of unity? These are all the e to the power I to k pi by n type numbers where the GCD of k and n is 1. So it is summation k greater than or equal to 1 GCD k and n 1 cos 2k pi by n. Okay, so I want to prove that. So I define fn, an arithmetic function, as its domain is natural numbers and its code is complex numbers. So my first claim is that the summation k equals to n e to the I 2k pi by n, which is nothing but the sum of all the roots of nth roots of unity. It turns out to be summation d divides n ft. Okay, so I just sum it just by grouping it in a certain particular way. If I define x naught as e to the power I 2 pi by n, so all the roots can be then written as x naught square, x naught cube, x naught 4, and so on. In general, x naught to the power k. So I have just summed up over all those roots based on the GCD of k with n. If GCD of k and n, that is x naught to the power k, I'm talking about this. If GCD of k and n is d, then I will put x naught to the power k in that part. So I have just defined another partition of these sets, and I have just summed up over all those partitions, cardinality of all those partitions. Okay, so or sum of those partitions, sum over all those partitions. Okay, now I see that summation d divides n, GCD k and n is d e to the I 2k pi by n. Now if k and n have GCD d, obviously d divides k, and thus k must be greater than or equal to d. So I can say that GCD of k and n equal to d is an equivalent condition as GCD of k by d and n by d equal to 1, because I have just divided the as much as possible.
আচ্ছা, ওই তুমি কি
have you said?
হ্যাঁ, okay, no, please continue.
Okay, sir. Yes, so I was saying that if GCD and k and n is d, then GCD of k by d and n by d is 1, and that is a very equivalent condition. And so I have that, and we have to just make a few substitutions here. That is, I am writing k pi by 2k pi by n as by dividing the numerator and denominator by d. Okay, so finally I get this expression, which is by 2k prime pi by n by d, which is nothing but just the expression of fn, but n is replaced by n by d. So we have this expression equals to summation d divides n f n by d. and which can also be written as summation d divides n fd, because these are just summing up all the divisors of n into reverse ways. That is, if the first one is summing over the divisors of n from the left side, then the other part is summing over the divisors from right side. So it is basically the same sum. Okay, now we have proved the claim 1, and we have the second claim, which is a bit easier. That is, I know that sum of all the roots of a polynomial is equal to the negative of the coefficient of the second highest power of x that is present in the polynomial. In our case, the polynomial of our constant is x to n minus 1, and it has the second, if n is greater than 1, then say so n is at least 2. So if we take x square minus 1, the polynomial is x square minus 1, so the second highest term will be x, the term involving x, but that is not here. So the coefficient of that second highest power is 0 if n is greater than 1. So the sum of the roots of this polynomial is 0. Now if n equals to 1, then the polynomial turns out to be x minus 1, and here the second largest term is the constant term, and which has a coefficient of minus 1. So the sum of the roots will be minus of this coefficient, that is minus 1, that is 1. So we see that this sum of all the roots, that is e to the power 2k pi by n, k equals to 1 to n, nth roots of unity, is just what the delta n is defined. That is, it is 1 for n equals to 1, and it's 0 for if n greater than 1. So we have claim 2 here. And now from one thing that Subhradip have earlier said, that mu is one of the special functions, because in some respect, as it is the only function that has the property that f star 1 is mu, if f star 1 is delta, and this function that we had taken as fn just satisfies the same property. We have the summation d divides n fd equals to delta n, because summation d divides n fd is equal to e to the power 2k pi by n, summation k equal to 1 to n, and this part, the left hand side, is equal to delta n that we have proved. So we have finally summation d divides n fd equals to delta n, and so it can be written as summation d divides n fd 1 n by d, because 1 n by d is 1 for all n. So it is basically f star 1, and that is equal to delta n, and we know that only function to satisfy this property is mu, so fn is equal to mu n. Now going to the claim 3, or the final step of our proof. It starts with a simple observation. We say that if GCD of k and n is 1, then GCD of n minus k and n will also be 1. This is very clear. If for example, take a divisor d, and d divides, suppose d divides n by n and k, and then if d divides n and k, then d also divides n minus k. So d divides n minus k and n both. So if any divisor divides k and n both, it also divides n minus k and n both. So as if GCD of k comma n is 1, so this way n minus k and n will also be 1. This simple observation simplifies our sum that we had. That is the sum of all the roots, primitive roots of unity, or nth roots of unity. That is, if we just change the index from k to n minus k, we know that that index is also in our set, because if k has GCD 1 with n, n minus k will also have GCD 1 with n. So if k is in our nice set that we want, n minus k will also be there. So I can just reverse the index. So it can be written as e to the power 2 n minus k pi by n. So it is nothing but e to the power minus I to k pi by n, because the n will cancel with the n in the denominator. It will give it's a minus I to k pi by n. So what it tells is that sum of the primitive roots of unity, nth roots of unity, is equal to sum of the conjugates of the primitive roots of unity. Okay, so now we have that. We can write the summation, the real part. We know that the real part of z is equal to z plus z conjugate by 2. So that is what we are doing here. We are just saying that this cos 2k pi by n here is nothing but e to the power 2k pi by n plus e to the minus I 2k pi by n by 2. And we're just taking the sum above, or in practically taking 2 out, 1 by 2 out, and we get that this summation k greater than 1, the sum of the primitive roots of unity plus sum of the conjugates of the primitive roots of unity. And we know that these two sums are same. So that will be 2 into the sum of the roots of primitive roots of unity, and these 2 will cancel with the 2 in the denominator, and will give our required identity, that is equals to fn, and which is equal to mu n. So hence we have the identity. So far, is there any question or any confusion regarding any part? Okay, I am just proceeding. If there is any question, feel free to jump in anytime. Okay, so this was a part where mu just appears in complex, in dealing with complex numbers. Or okay, one thing I forgot to mention here, these are there is a very much involved motivation behind dealing with these type of identities, because these identities occur when dealing with hyperatomic polynomials, because hyperatomic polynomials are just the polynomial which has basically the primitive roots of unity as their roots. So what we had shown in the identity, it is just basically sum of all the real part of all the roots of the nth cyclotomic polynomial. So that will be mu n. So that is an important observation, and it can help to write or know a particular coefficient. That is the second largest coefficient of the cyclotomic polynomial. That will be mu n. Okay. Having said that, we go to the another application. That is a very interesting problem. In respect to that, it has not, as such, it has no application right away, but it is an interesting problem, because this shows that the mu is not only uh, a thing that is required for theory. It is a very much the Mobius inversion formula that is very much useful manipulative tool that we have at our hands. We can compute or simplify different expressions by using this Mobius inversion formula. That is a very good application, interesting example of where it can be shown. So what this problem says, that we define a sequence here, and we define it because this summation form doesn't, it may seem that it is not defined. It is just saying one property of the sequence that the sequence satisfies. But this summation form is defined in such a way it at once defines the sequence also. That means it tells us what the terms of the sequence will be. That means it uniquely gives us the sequence true. Because if we in the first line we see that if we apply this looks as a perfect place to apply Mobius inversion formula, because we can treat 2 to the power n as an arithmetic function, and AD is also a sequence of natural numbers, which is not mentioned clearly. It is a sort of sequence of complex sequence. We assume that it is a complex sequence. Then it is also a function from a set of natural numbers. Any sequence of complex numbers is a function from natural numbers to the complex set. So it will also be an arithmetic function. Okay, so we have arithmetic functions in the right way that we needed to apply Mobius inversion formula, and we so did, and we get that we can see that an can be written as summation d divides m mu n by d 2 to the power d. Just we have applied Mobius inversion formula, and we see that this uniquely defines an, the terms of an. We can put in values of n and just compute it from this formula. So this uniquely defines an for us. Now, what this problem says, that we have to prove that n divides an. We cannot compute every an and then see if n divides an. We just have to. We must have a logic that true for all n. Okay. So we proceed as follows. We take the largest possible power of p that divides m as as mu pn. Okay, that is the largest possible power of p that divides m. That is, what this means is that p to the power m divides n, and p to the power m plus 1 does not divide n. That is all it says. Okay, so let n equals to p1 to the power, and this is the canonical representation of n. Okay, and we take a dummy variable, two dummy variables p and k, and we put pj as, we take any prime factor of n, say pj, and we put p equals to pj and k equals to kj. Okay, now we see what this sum tells us. Okay, now I am summing this over all the divisors of n, but I am categorizing them on the basis of what is the highest power of p that is inside d. So I have summed it like this: summation d divides m, nu p d equals to I. So I am categorizing it based on the fact that what is the highest power of d. For example, I have categorized like the vp nu p d is I. That means I am taking all those divisors at first, such that p to the power I divides d, but p to the I plus 1 does not divide d. So I am categorizing the divisors in such a manner. Okay, so I have just grouped the sum here. Now I can see one thing here. If p square divides n by d, then mu n by d must be 0. And that will be the case if I is less than equal to k minus 2. Because if I is less than equal to k minus 2, then I know that the power of p in d is less than equal to k minus 2. So in n by d, it will be k minus 2. That is, at least that the power of p in n by d will be k minus 2, that is 2. That means at least p square will divide n by d. So mu n by d will be 0. The terms for of I from 1 to k minus 2 will vanish because mu n by d would be 0. So only the term that will be remaining is that for which the highest power is k minus 1 and for which the highest power is k. These two terms will only survive, others will vanish. Okay. So I'm just writing this sum in a particular way. The first sum, I'm writing it in a particular way. So what I'm doing is that I know that the highest power of p dividing d is k minus 1. So I'm taking a substitution. I'm substituting d prime as pd. Now I know that if the highest power of p dividing d is k minus 1, the highest power of d dividing pd will be p to the power k. Or that is, oh sorry, it will be k. Because I have just multiplied one more p with d. So it will increase the power, highest power by 1. So I have taken a substitution d prime as pd, and such that d prime has the highest power of p dividing is k. And and the rest is same. Okay, now I am just substituting this d with d prime. Now we know that d is equal to d prime, so d will be d prime by p. So here the mu n by d will be mu p n by d prime, and this d here on the power of 2 will be 2 d prime by p. Okay, the rest sum is remain untouched. Okay, now one thing I must observe is that I know that the highest power of p in n is k, and d prime also has the same highest power of p. So n by d prime will have no other power of p left in it, because highest power of p in n is k, and highest power of p in d prime is also k. So the entire k part is cancelled. So p and n by d prime will have GCD 1, and mu is multiplicative, and I can just pull them apart, and it can write them as mu p into mu n by d prime 2 to the power d prime by p. And I know that mu p is minus 1, so the sum turns out to be this one. And I have just observed that what was all the point of all doing all these substitutions is that it turns out the index here looks just like the second sum, and I can just group them. That was all the point behind doing all these substitutions, because I want to make this sum look like this sum, so I can group them. So I have is summation d divides n mu p d equal to k mu n by d 2 to the power d minus 2 to the power d by p. Now I claim that I proved the claim afterwards and stated first because I was just eager to prove it. Okay, 2 to the power d minus 2 to the power d by p is congruent to 0 mod p to the power k. That I claim. This part will be true. Okay. Now suppose if p is equal to 2, then it is true right away, because we know that 2 to the power d and 2 to the power d by p, they respectively are divisible by 2 to the power k, because d and d by p are higher than k, because there are some p to the power something that is obviously greater than k. So it is pretty much clear that this will be true for p equals to 2. Now if p is odd, I can just take p to the, just say that what is d? D is some p to the power k into c, where c is number which has no p. Okay, so I can take 2 to the power p to the power k minus 1 c common here, and I get that 2 to the power p to the power k minus 1 c p minus 1 minus 1. And I can observe that this p to the power k minus 1 into p minus 1 is nothing but 5 p to the power k. So what I have is 2 p to the power k minus 1 c into 2 to the power 5k c minus 1. And I know that from Euler's theorem 2 to the power 5k is congruent to 1. So 2 to the power 5k to the power c will also be congruent to 1. So this one turns to be 0. Congruent to 0 mod p to the power k. And I have just thus proved that p to the power k divides this thing, this entire sum. And this was true for any pi, because I have proved it with a dummy variable, and this dummy variable can take up any pj. So this is true for any pj. So this sum is divisible by any pj to the power kj, and thus it is divisible by n. So, and this was the representation for an, so n divides an for all n. So this was the number theoretic part. So any questions from this part? Okay, I'll just move on. So it will be the last application. That is a very much theoretical one, but very interesting nonetheless. It's very much interesting because it is very, some sense it is elementary and some sense it is involved, both mixed in right proportions. Okay. So what we are dealing with is that we want to find out the probability that a random natural number is square free is this thing, 6 by pi square, or summation n equal to mu n by n square. Okay. And this 6 by pi square is a very famous expression, because we know that 1 by n square is pi square by 6 that we have memorized from long ago. We have memorized this. We know that it is a very interesting number. The fact that pi comes up here, that itself is a very interesting fact. What pi has to do with anything here? There is no circle. There is no as such circular arc coming here, but still it coming here. So it is a very interesting thing. Okay. So let's start the proof. So at the first, I have defined something that is of a set, that is the concept that is called the natural density of a set. So what natural density does is just extending the idea of the naive definition of probability, that is, if any element is equiprobable, what is the probability that I can have, or I can pick an element from a particular finite set. And that is what this natural density definition formalizes. It says that, or it's in some sense, it expresses the probability of picking a particular element, or making a choice from an infinite set as a limiting tendency of the naive definition of probability for finite sets. Okay, so we will appreciate the fact as we move on. So at first I define a set. So what the set is n belongs to n, p square divides n, basically the multiples of p square. So this is an infinite set. So I don't know how to deal with infinite sets as of now. So I look at a finite set, finite version of this set. That is, I'm looking all those multiples of p square which have which are less than a particular number. That means I am saying that I am looking at all those multiples of p square that are less than, suppose I'm saying n. I'm saying that all those multiples of p square which are less than n, because I know that natural density of a set just extends the definition of probability from a finite set to the infinite set by a limiting tendency. And this definition for a finite set is very much intuitive, from our naive definition of probability. It is very intuitive. That is what we have a certain number of elements that we can choose. So the number of possible events is finite, and what is the possible event of picking this particular one? So that will be just total number of favorable elements by total number of possible events. So that is a classical or definition that we have known from school for a finite set. So that is nothing outside our intuition. And what this natural density says, that we can extend this using a limiting tendency, a limiting concept, to infinite sets. And that is what natural density is. But it doesn't say it is a probability. It is a slightly different concept, that is natural density, because probability has a much more precise and in formal definition for infinite sets, and probability of occurrence of a particular event from an infinite set of events. Okay. So what is the probability that I pick a number from say?
Hello, Pratik.
Yes.
Can you please explain what you mean by natural density once again? I did not get
Okay.
it properly.
Okay. So by natural density, I mean that if I have a certain finite set, right? If for example I take the set of multiples of p square which are less than a particular given number n. Now I am saying that what is the possibility that I pick a number from this set that is multiple of p square? Say I have certain number of multiples. I know that I can count them explicitly because it is a finite set. Suppose there are, I'm saying that suppose there are m many numbers such that this multiples of p square, and they're also less than n, so there are m many of those. So what are the favorable cases in our case? I'm just talking about the classical definition of probability. So what are the favorable cases? That is, these m cases are favorable cases. But by cases or events, I mean the total set of events is the total all set of numbers, all numbers possible. That is 1 to n. From that is the all favorable cases, or sorry, all to entire sample space. And the sample space I am looking at, the favorable cases are only the multiples of p square. Suppose there are m many of those. I'm not going to counting how many of them are, just m many of those. So what our classical definition says there is that the number of favorable cases by total number of size of the sample space for a finite set. So that is what m by n, and that is what I am saying for finite set. Now this natural density concept extends this definition or the classical definition of probability for a finite set to an infinite set. But this is not exactly probability, because the probability has a much formal definition. I suppose, I don't remember at this point what is the formal definition, but I suppose from a probability course I took in genet course, I think there is a certain formalism that require or to define these concepts for infinite sets and so on. So I think this natural density is a concept which generalizes the classical definition of probability for finite sets to infinite sets by bringing in a limiting concept.
So like what is the, I don't know, what is the benefit of taking this definition of natural density as probability rather than the I don't know what the infinite case of probability will be, but what is the benefit of taking this definition of natural density over the classical definition of probability? Or what?
Okay, no. See that the classical definition of probability is not very much formal for infinite cases. It is only true for finite cases. No, because we cannot take that entire sample space size we don't have for infinite cases. So basically, what we have for natural classical case is for finite sets, and that is what we are sticking to for finite sets. Here also we are sticking to the classical definition only. What we are doing is that we are just extending this classical definition to the infinite sets by using the limit. But this limits thing is not now while talking on now, I think that this limit thing is not in general true, no, because we don't know exactly the structure of the sets. In this case we know, because we know the natural numbers and we have a certain type of limiting sense and over the set of real numbers we know how to do the limit. In general sample space we don't know what this meaning of limit is. So you cannot just generalize this concept of classical probability to infinite sets. For that we must require other formalisms to come in and just make sense of the fact, the limit. What does it mean by limit? But here, as we know that we have a certain structure to this sample space, and we are just exploiting the structure by introducing the limit concept, we can just straight away just extend the definition of classical probability to infinite sets. I think that I don't know exactly what.
So like then if we have a proper formalization of probability of infinite sets, then this will be consistent with
yeah, it must be consistent. I think so.
Yes. Okay, thank you.
Okay. Thank you. Okay. So continuing from what I had said, that is that you take a finite set, right? We finite set and the finite set is that number of multiples of p square, or the set comprises of all those numbers which are multiples of p square, but they are less than certain particular number n. And how many of them are there? I said while discussing that suppose there are m. Now I want to find what that m is. Now suppose I take this set Sn. I just want to formalize this thing, because by saying that, suppose take Sn. Sn is all those multiples which are greater than or equal to n. Now I know that this set has a lower bound, right? Because there will be a least such number satisfying this condition. So so as it is a set of natural numbers and it is non-empty. For in first and foremost, it is non-empty. So there will be a multiple of p square that is greater than or equal to n. So by well-ordered principle, I have a minimum. And this minimum, as kn is the minimum number, we know that p square kn will satisfy this criteria, right? So p square kn will be greater than or equal to n. But kn minus 1 will not satisfy this criteria. So p square kn minus 1 will be less than or equal to n. So I have this inequality. P square kn minus 1 less than or equal to n, less than or equal to p square kn. And I just can manipulate it, and to get that n minus p square is less than or equal to p square kn minus 1 less than or equal to n. and I divide the entire thing by np square. So I get that I have 1 by p square minus 1 by n less than or equal to kn minus 1 by n less than or equal to 1 by p square. So we see that what this kn is that kn is the nothing but the kn minus 1 is nothing but the cardinality of the set, or the m that I was talking about. That is the cardinality of the set which satisfies the conditions. That is, it is a multiple of p square and it is less than or equal to n, because we know that for kn, p square kn is greater than or equal to n. So that cannot satisfy the criteria. So up to kn minus 1 it is true. So kn minus 1 is the cardinality that I was talking about. So the classical probability definition of probability says that the finite set, the number of favorable cases is kn minus 1, and the total size of the sample space is n. So the probability, classical probability, is kn minus 1 by n. Okay, so this kn minus 1 by n is bounded by these two things here, 1 by p square minus 1 by n and 1 by p square, and limiting, taking the limit on both sides, we see that this probability, this classical sense of probability, as we increase the size of the sample space, in some sense tends to the number 1 by p square. And that is what we have defined as natural density, right? So the natural density of this set, that is the set of multiples of p square, is 1 by p square. That is, what is the probability that a random number picked from the set of natural numbers is a multiple of p square, is just 1 by p square. Okay. So now another thing that I will be needing is the Euler product. It's a famous expression, and it is a much more involved case. But and requires a bit of complex analysis, at least for sequence and series part. We need complex analysis for some criteria purpose, and we don't know complex analysis, so there's nothing problem, because we have assumed that this S is a real number, and for real we know almost all the criteria except the criteria for convergence of infinite products that I will mention when the situation occurs. Okay. Now suppose this product here, 1 plus p to the minus s and p to the minus 2s, I have just multiplied the entire thing, and I have just written it in the summation form, and that summation form looks like this: summation n minus n to the minus s, and I just want to see what these ans are. Okay, and I can clearly see that, and this multiplication is like, yes.
Can you continue this topic in the next class? It is already 3:23. 3 hours and 23 minutes.
Okay.
If you sir permit.
Sir.
Come together. Yes, I think not much is left, right? Maybe
yes, sir.
5 minutes.
The last part. The last, yes, sir.
Yeah. So please continue. Yeah, that would be over.
Confusion for the set of particles in this thing between P and
okay,
R.
so
they get something and they don't get something.
Okay, so
like the probability is that.
Yes, so the multiplication is I'm doing the multiplication like I do in a generating function, like you do in a polynomial, in case of polynomials. So we can see clearly that the coefficient of n to the power the coefficient of a1 is clearly 1, because we know that the coefficient of 1 by n.
Notations for RAM secret sharing. The one which we choose to use is the KLN RAM secret sharing, where KLN RAM secret sharing
So
the set of size K plus is the
yes, please continue. Yeah.
knowledge of the number.
Sir,
okay, so yes, so the coefficient of a1, that is coefficient of 1 by n. So how can you obtain 1 by n? So all the primes involved must have the power s as 1. So so you see that if we assume them as boxes, and each of those boxes have a particular s. For example, one box has 1 plus 1 by p plus 1 by 2 p square, 1 by p cube. Yes, 1 by p cube, and so on. Another box has 1 by 1 plus 1 by p square plus 1 by p to the power 4, and so on. And another box has 1 plus 1 by p to the power s, 1 by p to the 2s, 1 by p to the 3s, and so on. So how can I get n from here? 1 by n. So I must pick the second elements from each of these. I must pick all 1 from all those boxes having s greater than or equal to 1, and only pick 1 by p from these boxes, first boxes, because I want a product as p product of all primes, such that 1 by n occurs. So and all these coefficients involved are only 1, so that coefficient of 1 by n will be 1. And we can similarly see that a2 will be 1 and a3 will also be 1. Now I have to show that the one thing is that we must ensure that this thing converges, or this thing has a particular is a real number. So for that I proceed as follows. I just define as I need a concept of some kind of subsequence, and I define it by taking the sum for all those pi less than equal to k, some fixed number k, and I say that this sum converges to the entire sum as this k is made larger and larger. Okay, so I just go over this a bit quickly by saying that I am using here the rule of or a criteria for convergence that says that infinite product of say an converges if and only if summation log an converges, and I'm using that only because I have a product of the form 1 minus 1 by p to the power s, right? I have this type of product, right? So this type of product, if it has to converge, then the corresponding log sum of the log of these terms will be look like this. This minus is because it is a reciprocal thing, so it will be minus 1 will come out. Okay, so this series must converge, and I can see that this series, this term of this series, log 1 minus p to the minus x, is approximately p to the minus x, and this is nothing but log 1 plus x by x tends to 1 as x tends to 0, and then from that means, or in other words, log 1 minus p to the minus s by minus p to the minus s, it tends to 1 as p tends to infinity. Okay, so that is what this says, this definition says of approximation. Okay, so this is approximately this equal to this. So this sum, the log sum will be approximately equal to this sum, and this sum is bounded by the sum in summation equal to 1 to infinity into the minus s, because this is a subset of these elements of 1 by into the s type elements is a subset. So this sum will be bounded by this one, and this sum converges famously, we know, because for s greater than 1 this sum converges, we already know. So this sum will also converge. And now I have one more last thing to say about this convergence, is that this particular subsequence or a and k minus 1 or the subsequence terms, if we increase the k, we see here that the difference from the subsequence and the entire sum that we want to show is, we have already shown it is a convergence, but we want to show this is the limit of these fks things, is that we show that this difference is positive, it is decreasing, strictly decreasing, and it is positive. And we know that from monotone convergence theorem this must go to 0, right? Because it is strictly decreasing and it must go to the infimum, and the infimum is 0. That we can show here because we know that 1 by n to the minus s converges. So if we take the sum from a particular m terms, so mod n k minus 1 n to the minus s, and if we take the sum n from some particular number, large number m, then we can reduce this sum, make this sum less than some given epsilon. So this sum is decreasing and its infimum is 0. So it must converge to that point, and thus fks has limit zeta s, and so we have this identity. Okay, now the last okay, so this part I am just going over quickly, and this part proves, and I'm just skipping this part because I will then miss the main part. Okay, so this part here I am proving that this 1 by zeta s is just summation n equal to 1 mu n by n to the power s. The one thing that we must observe is that I can write this product like this, right? And this is nothing but 1 by n to the s. I have just proved it as the Euler product identity. I have proved it here, and this is nothing but this thing, just reciprocating the terms, each of the terms, respectively terms, and this, we get this one, right? And just multiply it, and we can prove the existence or the convergence of these sums, because each of these sums are bounded by 1 by n to the power s. So 1 by n to the power s is convergent, so each of these sums are convergent, right? So in some way, and this product is also convergent because of the criteria that we have mentioned before. So all these things here that we have written here are valid and meaningful things, that is, they are all convergent sums and products. So this thing we have at last, we see that we just observe the signs here. We see that if there is only one prime factor, so there is a minus sign here, and it has two prime factors, it has positive sign. So if distinct primes, I mean, it has n has PIPJ form, so it will be mu of PIPJ is 1, and so I see that it observes the definition of mu n. So I can see not a rigorous one. This proof, the last line is not a rigorous one, but we can observe one, and pretty much to mass satisfaction, we can say that this is equal to summation n equal to infinity mu n by n to the power s. Okay, so the last part is that this Euler product that we had is what is the actual probability of getting a random number which is square free. So how can you prove that? We have already proved that getting a random number which is divisible by p square is 1 by p square. So what is the probability that a given random number is not divisible by 1 by p square? That is a complement of that event, that is 1 minus 1 by p square. Now I have to, if we want to ensure that a random number picked is not a square free number, so it must not be divisible by any p square for any prime p. So I must have the property that it must not be divisible by 1 minus 1 by p square, and also must not be divisible by 1 minus 1 by q square. It must also not be divisible by q square. So as these events are independent, because divisible by p square has nothing to do with divisible by q square, right? So these are independent events, and I just multiply them, and again there comes some sense of convergence here, because we are dealing with infinite products, and we know that this infinite product converges, right? Because we have shown it for any s greater than 1. So this product in particular converges. So again, by using the classical definition of probability, we are extending this using the natural density concept, we're extending this notion of probability to infinite subsets, and we get that it is the probability is nothing but p equals to prime 1 minus 1 by p square. So what we had before and what we just proved just gives our result. Okay, so right, we know that 1 minus 1 by p square is just the Euler product representation of zeta 2, and zeta 2 is nothing but 1 by n square summation 1 by n square n equal to 1 to infinity. So we have that, and we know that this is okay, sorry, I've made one mistake here. The reciprocal of 1 minus 1 by pi square is zeta 2. So 1 minus 1 by pi square is 1 by zeta 2, that is 6 by pi square. Now just for all the claims and lemmas that we have proved so far, just gives our result summation equal to 1 to infinity mu n by n square, that is 1 by zeta 2, and that is in turn 6 by pi square. So this was the end. Any questions so far?
Yeah, any question? So the last part was little bit, he was in a little bit hurry because we are running out of time. That's true, but some tough thing he has explained and in a nice way. So any question or comments if you have? So he is your batchmate, so you can directly contact him, or anybody if he or she wants any clarification, you can send him email or message. So